Have you actually wondered why chaos exists in nature? If you look around your life, chaos is around you. Whether you can find it in your body, you can find it in your career, or it's just something around you, everything around you. Maybe the bad traffic in the morning, or maybe the leaves that goes down during fall, or whatever in your life. It seems that your life is dictated by chaos. So, have you ever wondered whether chaos can be quantified mathematically and numerically? Yes, it can. And through the thermodynamics parameter, and through the beautiful law in physics, and through the beautiful thing and concept that we know as entropy. Welcome to Entropic Chemistry. And my name is Dr. Vasut Pornpacharapong from the International College of Digital Innovation, Chiang Mai University in Thailand. So, although you may hear digital innovation, you may like, what? Digital innovation, isn't that AI? And why am I talking about chemistry and physics here? Well, they actually relate more than you think, alright? So, in this episode of Entropic Chemistry, it's a part of the first season called Entropy. And during this season, I will discuss from the theoretical beginning of entropy down to where entropy exists in life from small scale to the large scale of the universe and the cosmos. So be prepared to be thrilled with the concept of entropy together, and then I will help you explore the world of entropy and why nature seems to be full of chaos. Alright, so forgive me if my language is so accented, if my English is accented. So English is not my first language, but I'm trying to make it easy for you, okay? So please stay here and bear with me. This series of lecture will be unscripted, so I will try to talk everything from my brain, alright, as far as I remember. So there might be some pauses, there might be some silence, so bear with me. But this is not meant to be boring. This is actually meant to give you some stimulation exercise for your brain, okay? So brace yourself. It's not going to be a boring lecture in the physical chemistry classroom, but it's going to be me, as a former chemist, walk you through the concept of entropy, alright, and how entropy actually relates to our life and why should we know about it. Even though you are not a scientist, everyone should absolutely know about entropy, alright? So I'll walk you through gently, and if you're ready to explore the wonder of the chaos of the nature, please join me in the first episode, alright? Entropy. So this is the way that the nature quantified chaos. So welcome. So let me erase this first before I talk about the concept, alright? Alright, so the board is now clear. So before we start to dive on the concept of entropy, so let me introduce you to the jargon, the first thing that you want to know, but it's not that heavy. So it's this very word that we know in thermodynamics, alright? So S-Y-S-T-E-M, alright? So what I'm talking about here is system. So when you hear the word system, what do you actually think about? So if you have taken science courses in the past, you may think about the system in the scientific point of view, alright? So maybe a glass of water, water in the glass, or maybe seawater in the ocean or something like that. That's true in a sense because you are now talking about scientific system. But have you ever thought beyond science? Because system actually exists far more than science as well, beyond the boundary of science. So system could be actually scientific system, alright? Which is something you may be kind of familiar with in school, or it can be anything beyond science. All right, because if you extend the concept of system, it actually sort of applies everywhere. So I'm not going to talk about a scientific example for system. What I'm going to talk about is the concept of system beyond science. All right, so have you ever actually thought of that? So what exists beyond science, and what kind of thing do we want to study? So, sorry, system is actually something that you want to study. All right, so when you define a system, you define a scope of the thing that you want to study. For example, the example of the water in the glass, right? So maybe you are a scientist, you want to observe how the water in the glass behave. So how does it flow? How does it change the shape along with the container or something like that, all right? Or if you want to study ocean, all right, seawater in the ocean, maybe you want to study the tides, or maybe you want to study the waves, or something you want to study, or sometimes you want to study the ecosystem right in the ocean, all right, the coral reefs, the kelp forest, etc., all right? That's the system in the scientific sense. What about something beyond science? Well, what about your emotion? So let's say you are exploring your own emotion. Today, I just feel so sad, but tomorrow, oh, I'm so exciting. I'm gonna learn entropy with Dr. Vasut, so on and so forth. So your emotion can change by the day, and if you want to study your own emotion, then your own emotion also becomes a system. All right, so it can be something as abstract as emotion. What else do you think? What could be the example of system beyond the scientific definition? Okay, besides emotion, maybe you can think of social media, all right? So, how is that? When we talk about the social media, we talk about platforms like Facebook, Instagram, TikTok, or YouTube, anything. There are so many platforms nowadays, all right? So you may wonder how these platforms actually map their friendships. So they turn all these relationships into the mathematical abstractions like graph theory or something like that, all right? So when these systems want to explore the relationship landscape of the users, so they look into the graphs of the relationship of the people, all right? So they are looking into the mathematical abstractions. All right, so basically, you can actually think about the mathematical abstractions as some kind of system that you could study as well. So it's not just something you could physically see, or it's not just something tangible. It could be something really abstract as well. So the term system is actually very wide, all right? It could be anything that you want to study, really. So just define something you want to study. Whether it's scientific or not, it could be part of the system. All right, so now you understand the concept of the system. So there are three kinds of system. All right, so that's a strict thermodynamic system. But this concept from thermodynamics actually extends to all kinds of system, in my opinion. So how do I talk about it? All right, so what are the types of system that exist in the thermodynamics definition? All right. So there are three types of system. Sorry, my typo. Three types. Sometimes my hand can just go faster than my head. Forgive my handwriting, okay? All right, so there are three types of system. So if you are the student from thermodynamics, you can answer this question very quickly, of course, but if you are not, I'll help you along, all right? So the first type of system is called the open system, all right? And the second type of the system is called the closed system. while the third type of the system is called the isolated system. So we have defined 3 types of systems. So have you ever wondered how are they different? So the differences are in the adjectives, all right, in how the system is defined. So what about the open system? So let's take a look. So I define an imaginary box. So sorry about that. Whoops. I define an imaginary box. So forgive my drawing. Like I said, my drawing is not the best in the world. So sorry if my drawing is bad. So this is a kind of hypothetical box, all right? And this box is a system. So you can see that we have a lid on top, all right? An open system is just like an open box, all right? So if you put anything inside the box, so let's say you put some balls in the system, all right? So if this box is open like this, it's very easy for you to take all these balls from the box, all right? So basically, these balls are the tangible things that can be taken out of the box, all right? So you can see that in the physics and chemistry, of course, when we define open system, we define it by the ability to exchange particles and energy between the system and the surrounding, all right? But how do you actually extend this to any kind of system, scientific or not, all right? I would say the ability to exchange tangible object versus intangible objects, all right? So it's sort of the same. So what I'm trying to do is trying to extend the concepts from science to something beyond that, all right? So because in my opinion, I honestly believe that thermodynamics is not just about science, all right? Science is something that explains the nature, but the entire concept of science, actually, if you think about it itself, it could extend beyond the world of science, beyond the world of rigid explanation of rules of nature alone. So if you try to think about it and link to reality, it's actually much more fascinating than you thought, all right? So let's actually, before I go off tangent so much, let's go back to the open system, okay? So for open system, basically, it's just like an open box. You can take off the balls like this. And what about some invisibility, intangible things inside, maybe the air or maybe some kind of energy, all right? So these exchange freely between the box and something outside the box, all right? So that's an open system. Now, what about the closed system, all right? So what I'm trying to do here is I will remove this lid and I close the lid right here. So now an open box is closed, all right? So if the box is closed, can I take off the balls from this box? No, all right? So when you are in the closed system, you lose the ability to take off the tangible things, all right? So basically, you cannot take out the balls, but there might be something invisible, intangible that can leak out of this box, all right? So that's the closed system, all right? Now the tricky part, isolated system, all right? What is the isolated system actually? Let me recap the physical definition of open and closed system, all right? So for open system, in physics, it strictly says that the system could exchange particles and energy between the system and the surroundings, all right? So I swap matters and energy with tangible versus intangible, all right? They kind of map. And then when I talk about the closed system cannot transfer matters, but can transfer energy, all right? So when we map to the concept of tangible versus intangible, it's matter that cannot escape into tangible things that cannot escape the box, all right? But some intangible thing may sort of leak out of the box in the closed system, all right? So for isolated system, it has to be so isolated from the surrounding. So let's imagine that instead of this box with the closed lid, now I wrap this box into the bubble wrap. All right, so this doesn't look like a bubble wrap, so let me actually label it. So basically, you just wrapped the entire box in a bubble wrap. All right, so it's not just that all the balls cannot exchange outside the box. It's so insulated inside the bubble wrap that the entire box is just locked inside that bubble wrap forever. That's the isolated system. All right, because in physics, isolated systems cannot exchange matter or energy between the system and the surroundings at all. All right, so in the grander scheme of things, if you think about our own Earth, all right, it may look big compared to your own scale, but compared to the entire universe, our Earth is just much, much smaller than a tiny drop of water in the ocean because the universe is just so vast, all right? So what exchange from the Earth to the universe is so negligible in the cosmic scale, so we can treat in that grand scheme of things that our Earth is just an isolated system in a much, much larger universe, all right? So that could also be the interpretation of the isolated system as well. So it's not just a universe, but it's something so small compared in scale, all right? Because the exchange of that system compared to a very, very large environment is negligible, all right? So those are three types of system that we consider, all right? I hope you don't have any questions. So if you have any questions, you can just go back and look again in the systems, about the systems, all right? So sorry if my English is so bad, but it's okay. Let's move on, all right? Now that we talk about the system, you may wonder, why haven't I started about entropy yet? Why am I rambling about all these? Because if you don't understand all these, I mean, what I'm gonna say later on is just gonna be some mumbo jumbo to you, and you won't ever understand it, and it will be very hard to follow. So once you master the three types of system, we will talk about the tendency of chaos, all right, and why chaos exists, all right? So now that we talk about the system, we'll talk about chaos now, all right, and what does it look like? So let's actually talk about a classic example, all right? So I'm just drawing a glass of water so that you can understand it better, all right? A glass of water. So we have a water like this, all right? This is not a closed glass, so this is an open system, all right? So what am I gonna do here? So what happens if I put some kind of burner below this water? So what I'm doing here is I'm heating water in the glass, all right? So what happens when somehow I heat long enough? What happens to the water? So the water will start to boil, all right? The water will start to boil. So you start to see vapor coming off this, all right? So do you see something here? Why am I trying to draw this, all right? So if you take a look at the red thing that represents liquid water, can they move freely? No, they kind of stay in the glass, right? But what happens when the water boils and turns into steam? So you can see that steams move around freely, all right? So what do you do when you turn water, liquid water, into steam? You basically increase the chaos of the system, all right? The system becomes more disordered. That's how you are taught about entropy, all right? In most introduction to physics and chemistry in college and universities around the world, that's how you got introduced into the concept of entropy, All right, you got introduced into the concept of disorder. All right, and by turning liquid water into steam, you increase the disorderliness of the system. That's not kind of wrong. All right, but if you actually remember entropy as just disorder alone, you are doing a disservice to the beauty of the entire subject of thermodynamics, all right? Because there's so much behind the word disorder alone. So you may wonder what actually happens behind the scene, all right? Because it's actually a beautiful thing. So let me actually talk about some analogy to you, all right? So let's say I remove this, all right? So I am a marathoner, so I run marathons. So I will draw a picture of a runner, all right? Just a pictogram, sort of. I hope this looks like someone who runs, right? So let's say this is a marathoner, a running marathoner, of course, all right? He's running at some pace. Let's say he's running 10 minutes mile. Or for you folks in the metric countries, that's about 6 minutes per kilometers. All right, so that's the original pace of this guy running marathon. All right, so let's say somehow there's some invisible feet kicking him. All right, so there's some invisible feet kicking on this marathoner. So by that act, that invisible feet is sending the energy into the marathoner, and that marathoner got that energy, and somehow with that energy going into the marathoner, he ran faster. The pace drops from 6 minutes per kilometer down to 5.5 minutes per kilometer. So he ran faster, all right, because he got more energy, all right. Or similarly, what I can do, instead of having some imaginary guy kicking this guy, what I can do is, let's put the burner, all right, close to the marathoner, all right. So basically, I am giving this marathoner a thermal energy. So what's going on here? So he feels like, oh my gosh, my feet is on fire. It's so hot here. So what's he gonna do? He's gonna run faster, all right, because he's got that thermal energy. So the pace also dropped as well. All right, so that's the energy of the marathoner. Now I will remove this marathoner. Instead, I turn this marathoner into a water molecule. H2O, all right? Same things here. The water molecules may move at some particular speed, but with the heat, all right, with this heat going into the water molecule, it moves faster because the kinetic energy of molecules follow this rule, all right? So this is the kinetic energy of ideal gas molecules, all right? 3/2 times Kb times T, where this K sub B is called the Boltzmann's constant. And this name Boltzmann will come later today, of course, and I will see, and you will see why is Boltzmann appearing here, all right? Boltzmann constant. And T is the temperature. So you can see here that the kinetic energy of a molecule is actually equal to this in the case of the ideal gas. All right, I want to talk about what ideal gas is, but essentially I want to drive you into this concept of the kinetic energy is directly proportional to the temperature. All right, so what does this tell you? It tells you that molecules moves faster with higher temperature. All right? So what happens when the molecules move faster? It became what? Chaotic. That's correct. So once a molecule moves faster, the move pattern becomes more erratic. All right? So thereby, when you increase the temperature, you also increase the disorderliness of the system as well. All right? So that's how entropy is related to heat in the first place. That brings you to the concept of entropy that you normally learn in thermodynamics. All right? So let's talk about this nifty equation right here. So if you are a science student, you may have remembered this equation. All right? ds equals dq reversible over T. So actually, this is the definition of entropy that is normally talked about in thermodynamics classroom. All right? Entropy is not even defined as a variable. All right? It's defined as a differential. Over here, ds. All right? But if you look at this equation, you may see something. All right? So ds, which is the change of entropy, or should I say, if I want to say it rigorously, let me write it so that everyone can follow along. All right? So infinitesimally small changes in entropy. All right? So this infinitesimally small change in entropy is related to this thing right here, Q, which is heat. All right? So I can say the same thing here. Infinitesimally. Oh my God, I hate this word. It's so long to write, and English is not my first language. It's not just a normal heat, in what we call the reversible heat. All right, why reversible though? So that depends on the actual formulation of entropy in thermodynamics. All right, I actually won't dive into too much detail. All right, because I don't want this lecture to be a thermodynamics lecture. I just want you to understand the main concept of entropy. All right, so you can see this equation right here. All right, and this is the Clausius definition of entropy. So you can see that ds is related to dq reversible. What does that mean though? I just talked about the fact that heat introduced disorder through introducing the more erratic pattern of movement of particles. All right, so you can also see in this pattern very clearly. All right, so if the system has a lot of heat coming into it, so basically what's that heat going to do in the system? So that heat is going to be dissipated inside that system, and the molecules, the particles, and anything inside the system will take note of that added heat, dissipated heat. All right, and those heat will affect all the particles, all the atoms, all the molecules inside. And of course, due to the kinetic law, they will move just faster. And because they will move faster, thereby they will also move more erratically. So that's why the more heat being introduced in the system, then you have more entropy, and thereby your system become much more chaotic. All right, that's how chaos is quantified. All right, but there's actually one more beauty about entropy, because this is not the only way we define entropy. All right, but before we talk about the second way that we could define entropy, let's talk about the reverse case. All right, so you can see here that if we introduce more heat into the system, you increase the disorder by having the more dissipated heat causing molecules, atoms to move faster inside the system. And by moving faster, they move much more erratically. All right, so let's actually talk about the reverse case. What if you remove heat from the system? So when you remove heat from the system, dq becomes negative. All right, so when you remove heat from the system has less heat going around. All right, and when they have less heat going around, all the molecules would just move slowly. All right, so it's just like when you are running and suddenly you slow down. All right, so what happens when you slow down? You become much less erratic. Your heart rate drops. All right, it becomes less like, oh my gosh, am I gonna pass out soon or something like that? So your heart rate is gonna drop. You feel like the order, the control to yourself returns. All right, same goes for the system. So for the physical system. So when you remove the heat, then the system will have less heat passing around. So they move slowly, they move more slowly, the molecules, the atoms, and then they have far less erratic pattern to move around. That's why the entropy decreases. So that's how we relate entropy to the concept of disorder. All right, but since this is normally how you are introduced to the concept of entropy, I'm sure this equation leaves you a lot of question marks, all right, because you may not be able to map clearly how is this thing relate to disorder, because this relation seems to just relate to heat. That's just one step thinking. All right, so now let me actually show you one of the alternative definition of entropy that might change your understanding of entropy forever, because not everyone could take statistical mechanics, all right, which is normally in a more advanced course in thermodynamics. All right, so let me erase this and introduce you to the alternative way that you can calculate entropy. All right, so let me write down this equation. It's very neat. We still use this symbol S for entropy. And this equation, we set that equals to still K sub B, which is the Boltzmann constant we talked about, times the natural logarithm of this new variable, omega. All right, and the key to understand this definition is omega. All right, what is omega? By the way, this omega is usually taught in the class, and we usually call that microstates. It's not microstates in the geopolitical sense like the Pacific Islands. No, not those. It's in the physical sense. All right. And actually, this is the beauty here, because the concepts of microstates, while originally conceived for physical systems, you can actually think about this beyond physics, beyond chemistry as well. And this equation came from a famous physicist who had a very tragic life story. This equation came from a scientist whose name was Ludwig Boltzmann. Yes, you see this name came again, all right? And because this K sub B is a constant that is actually named after him, all right? So he was tragic because he came up with this very interpretation of entropy, but it was very novel, too novel for his time actually, and this was recognized before he died. Sorry, not before, after. So this equation was recognized for its brilliance posthumously for Boltzmann, which was a sad story, but it changed the way that we view entropy forever. Well, I talk about it changed forever, but how does it change? I'll bring that to you in a moment, all right? The key thing that changes how we view entropy lies in this guy right here, the number of microstates. So how am I going to explain that to you? So basically, let's just say that if you are a math major, or if you are good with math in general, let me ask you this. if you have 2 coins, all right, if you have 2 coins, so how many possible outcomes can you have by tossing 2 coins together? Well, you can have outcomes like one coin being head, the second coin being tail, or you can flip the order, or you can have both heads, or you can have both tails. All right. So basically, if you flip 2 coins, you have 4 possibilities of outcomes. All right. Now, if you have 3 coins, so how many possibilities that you can have? All right. A lot more. All right. So that's combinatorics. And what if you have 5 coins tossing around together? Then you actually have far more possible outcomes. All right. So those outcomes that you have can be thought of as omega, or the number of microstates. All right. So in this formulation of entropy, you don't actually look into it in the way of heat through the interpretation of how the heat flows in or out of the system. You actually view entropy in how many possibilities can the system be configured itself. All right, so that's the beauty of this formulation of entropy. And we call this type of entropy statistical entropy. Because you look at this entropy through the pure lens of statistics, not heat, not thermodynamics, but pure statistics, really. All right? But we just talked about entropy through the definition of thermodynamics through heat. All right? You may wonder, now that I introduced the statistical entropy, are these two related to each other? I use the same variable S to identify entropy. But do they relate? Think about it. How? So, how does the entropy derive from the closest definition? This guy is ever related to this? Well, you have to think in terms of the kinetic energy. All right? So basically, if you increase the temperature, I just told you earlier that it makes the particle moves more erratically, all right? And by moving more erratically, you have more possibilities to occupy the configurational space. Well, my language may actually sound still kind of scientist-y, so let me actually illustrate it this way, all right? It might make more sense to you. So I stopped talking about temperature. I will talk about pure velocity. All right. So you have one particle, this red dot right here. You start out from one particle with 0 velocity. So we start out from this. So can you guess how many possible configurations can this particle take? Just one, right? Because it stays just like that. There's only one possible configuration. So the number of microstate is just one. So if we plug this definition right here, S equals K sub B times the natural log of omega, where omega in this case is just 1. So in this case, this system has a perfect order. It doesn't move. It doesn't have any possible microstates except that one. All right? And that's actually what we call the third law of thermodynamics, where the perfect crystal has 0 entropy. See? That's really beautiful. All right? Now, I will crank up the velocity scale. All right? It's no longer 0 now. So Now the velocity becomes non-zero. So can you guess what would the entropy be in this case? It's not going to be zero, right? Since it has a non-zero velocity, it can move, all right? So, and it can move through so many directions, all right? So maybe it moves here, 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 it moves here. So you can see that the number of possible microstates, it's not just one anymore, it's many, all right? So if we plug this in to the Boltzmann's equation of entropy, all right, this omega is far larger than 1 now, all right? So S, the entropy, is now more than 0, all right? And if you increase the velocity even more, you are increasing the erratic pattern, the probability of the system of occupying even more microstates, all right? Thereby, you increase the entropy even more, all right? That's how the nature quantify chaos, because entropy, if you look through the Boltzmann's paradigm, it's purely statistics, all right? So it's not all about heat, it's purely statistics. And because entropy can be quantified and can be thought of something related to statistics, so the concept of entropy itself now moves beyond science into so many things, all right? So now people talk about what we call information entropy, something like, okay, so if the information is conveyed perfectly, that means that information has 0 entropy, because the people who got that information can just deduce everything. But then, if you convey the information and then the people who's going to receive on the end don't have any idea what it's going to be like, then the information entropy is very high. So you can see here that this concept of the statistical definition of entropy extends into information theory, and not just that, there are so many concepts related to entropy. For example, life itself, all right? So we, human, animals, plants that exist on this earth, we actually are the engines that increase the entropy of the universe. How? We'll discuss about that later in this season, all right? And it's not just that. Everything we do, even though we are trying to make our life more order, even if we want to keep our room tidy. So we are not decreasing the entropy per se. Yes, we might decrease the entropy of something in outside, but in fact, we unknowingly also increase the entropy of the universe. And the term here, increasing the entropy of the universe, is actually the universal law that drives things, that governs everything that we do, that governs everything that the nature exists. So that's how entropy is cool, because entropy is not just chemistry. Entropy is inherently statistics. And in the later episodes in this season, we will explore together why entropy is being applied to so many things. But before we dive into that application, since I come from the chemistry background, so basically I want to really explain the phenomena in chemistry through the lens of entropy in the next episode. So stay tuned for next episode, because we will talk about how the chemical reactions are governed by entropy and thereby by chaos. All right, because that concept is going to be quite eye-opening to lots of chemists too, because I would say chemistry is not just about beakers and instruments. So basically, chemistry is math and stat, really. And I want to really convey this perspective to everyone. But math is not that difficult too, because inherently, math is not about equation, it's about the way that we understand things intuitively. All right? So that's going to be the gist of the shows in Entropic Chemistry. I explain chemistry, I explain the natural phenomena through the lens of mathematics and physics, but then I will also explain the math and physics in a way that is intuitive, because that's not about equation, it's about how we understand things intuitively. That is entropic chemistry. So stay tuned for the next episode on April 1st, 2026. So thank you for watching, and please subscribe for our channel Entropic Chemistry. So thank you everyone for watching, and I hope everyone enjoy the rest of your day. Thank you and goodbye. Stay tuned for next episode. สวัสดีครับ